Welcome back everyone, Houston Math Prep here. We're going to use integration to compute some Laplace transforms for common functions that you might see at the top of a Laplace transform chart from differential equations. We've got 6 examples that we're going to do here. We've got Laplace transform of 1, t to some positive integer power. We've got e to the at. Sine of kt, the Laplace transform for cosine of kt works just like this one, so if you want to check out this one, you can just adapt for cosine of kt. They also have hyperbolic sine of kt, sinh of kt, cosh of kt. The hyperbolic cosine function works just like this integral as well. For our first one here, we have the Laplace transform of 1, so remember that the Laplace transform is actually going to be, it's an integral transform. The bounds are from 0 to infinity of our f of t, which in this case is 1, times e to the negative st dt. So since we have 1 as our f of t, this integral is actually just going to be simply our exponential there, e to the negative st dt. Now because we have an infinite bound, this is technically an improper integral, so we want to go ahead and say the limit, I'll go ahead and call my upper bound b, so we'll say from 0 to b, as b approaches infinity of this e to the negative st. Remember that infinity is not a real number that we can just plug in and do arithmetic with, so we need this limit as b approaches infinity. Let's go ahead and do our integral. So we'll have the limit as b approaches infinity. Now this exponential, since we're integrating dt, this negative s is a constant multiple in here. So when we take the antiderivative of e to the negative st, the reciprocal of this constant multiple comes out, so we get negative 1 over s coming out, e to the negative st, and our bounds are from 0 to b. Let's go ahead and plug in our bounds. So in our first one, we'll still need the limit as b approaches infinity. And if we're plugging in b for t, because we integrated dt, notice that this exponential has a negative in it, so I'm going to go ahead and bump this into the denominator. We'll say negative 1 over s, and then this e to the st, which becomes e to the s times b, is now in the denominator. So that's our upper bound, minus what we get when we plug in our lower bound, so we'll get negative 1 over s. And then if I plug in 0 here and put this in the denominator, this becomes e to the 0. Now this limit as b approaches infinity, we have exponential growth here. This is going to approach some infinite value on the bottom, so we have a constant over an infinite value. We're going to get 0 in this first part. We have minus negative, so that will give us plus. E to the 0 is 1 here, so we just end up with 1 over s. And that is our Laplace transform for 1. So the Laplace transform of 1 is 1 over s. Looking at our second one here, Laplace transform of t. So that will be the integral from 0 to infinity of t, e to the negative st dt. We're going to go ahead and do this with integration by parts. So we'll say u is equal to t, and dv is equal to e to the negative st dt. In that case, then du is going to be dt, and v will be negative 1 over s, e to the negative st. If we go ahead and plug all that in, so remember first we'll need the limit as b approaches infinity. Here we'll have uv, so that will be negative t over s, e to the negative st. And that will be evaluated from 0 to b, minus the integral of v du. Now notice that v is negative, so minus v du will actually give us plus here. This 1 over s is a constant, so I'm going to go ahead and bump it out in front of my integral. Remember, this is also from 0 to b still. E to the negative st dt is still left as part of v du. And then we'll just need to evaluate this integral here. Let's go ahead and do that. So we'll have the limit as b approaches infinity, then of what we already have, negative t over s, e to the negative st. Now, the reciprocal of negative s comes out, so we'll get negative 1 over s, joining this 1 over s we already have, so we'll say minus 1 over s squared, e to the negative st, and we'll evaluate that from 0 to b. So if we go ahead and plug in b. I'm going to go ahead and bump my e to the negative st and make those e to the st in the denominator. So if I plug in b, that would be negative b over s e to the sb minus 1 over s squared e to the sb. We'll take the limit as b approaches infinity of that, minus what we get when we plug in 0. If we plug in 0, this t, no matter what else we have, that's times 0, so we're going to get 0 for this first one. And then here, I'm going to get minus 1 over s squared e to the 0. Now over here, with the limit as b approaches infinity, we have polynomial growth and exponential growth. Exponential growth is faster than polynomial growth, so the bottom's going to grow infinitely more quickly than the top, or you could just use L'Hopital's rule on this here one time. This is also going to be infinite on the bottom, but we have a constant on the top, so both of these go to 0. So we get 0 minus 0 minus 0. Here we get minus negative, so that's really plus, and then we get 1 over s squared there, so it turns out our Laplace transform of t is going to be 1 over s squared. We're now going to do t to some positive integer power just as a rule. So think about, this could be t to the 4, t to the 6, t to the 15, t to the 100. But so what we'll do is we'll think of this as the integral from 0 to infinity of t to some positive integer power, e to the negative st dt, right? This is our function of t. I'm going to go ahead and use the tabular method here, so my u and my dv, and then this will be my positive negative 1 if you're familiar with the tabular method. So for u, I would choose t to the n. For my dv, I'm going to choose e to the negative st. I'll assign my alternating signs here down a ways. So when we take the derivative in this column, we'll get n t to the n minus 1. If I take the derivative again, I'll get n times n minus 1, t to the n minus 2, etc. Maybe I'll go ahead and stop there in that column. So if we're integrating here, we will keep getting a negative 1 over s coming out. That's the reciprocal of the constant multiple in there. So we get negative 1 over s e to the negative st, then we'll get 1 over s squared e to the negative st, and then after that we would get negative 1 over s cubed e to the negative st. So if we look at our first term, we're just going to do a few of these terms, and then we will see if we can find a pattern. So we have t to the n times negative 1 over s exponential times positive 1. So I'm going to start down here. I'm going to have my limit as b approaches infinity out front. So my first term is actually negative t to the n over s, e to the negative st. The next diagonal in my tabular method here, it's going to be negative again. We have n t to the n minus 1 over s squared, and then we have the exponential also. So negative n t to the n minus 1 over s squared times our exponential. We have our last one, and then we'll just sort of expand from there. It's negative again. We have minus, we have n minus 1 came out. We have t to the n minus 2, all of that is over s cubed, e to the negative st. We're going to just go ahead and say dot, 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 the pattern continues, and then we'll think about if we can establish a pattern from here, from 0 to b. Okay, so let's start here now by thinking about what happens when we plug in b. So if we have the limit as b approaches infinity, and I plug in b everywhere there's a t, I'm going to get negative b to the n on top, and on the bottom, if I bump my exponentials down, I'll get se to the sb minus, then I have n times b to the n minus 1 over s squared, bumping my exponential down again, e to the sb minus n, we have an n minus 1, then we get b to the n minus 2 over, now this is s cubed, e to the sb. The pattern would continue. Let's go ahead and think about what happens when we plug in 0, minus when we plug in 0. On the top, I'm going to get 0 every time I have a t term, right? Now these t terms are going down by 1 power each, but so I'm going to get some zeros to begin with. Up until the very last term, right? Think about this eventually maybe becomes t cubed, and then t squared, t to the 1, and then there is no t, so there's nowhere for me to plug in 0. And what would I have on top? Well, I would have n, and then n times n minus 1, and then this n minus 2 would come out, and then an n minus 3. And we're actually building a factorial on the top, right? So this would be minus n factorial. And on the bottom, what you might notice, think about what's happening with the n's versus what's happening with the s's. Here, no n, I have a single s. Here's an n, I have s squared. Here's n and n minus 1, 2 terms from our factorial, but I have an s cubed, that's 3 copies, right? In the next one, if I have n minus 2, that would be 3 pieces of my factorial, but then I'd have an s to the 4 in the next one. So the power of s that we get is actually 1 more than whatever we have for the number of things we're multiplying in our factorial. Let's go ahead and look back at this limit now. You'll notice that these are all indeterminate forms. We have infinite growth on the top and the bottom. The bottom is exponential growth, and all of these are going to go to 0. But another way to see this is if you take L'Hopital's rule for this, on the top, the derivative would give you this here. And the derivative of this would give you the next numerator there. So on the bottom, the same thing is going to happen. The derivative of se to the sb, if you think about it in terms of b, then an s would come out and another s would come out. And so really, this term is going to have the same limit as this term, the same limit as this term, etc. The power on the top is getting smaller. We just keep having exponential growth on the bottom. So we know that all of these are going to be 0. So the entire thing up here becomes 0. We get minus, and the only thing that's non-zero in the second group here is this negative n factorial over s to the n plus 1. And minus negative, of course, means we get positive, so we get n factorial over s to the n plus 1. And that is our formula for the Laplace transform of any positive integer power of t. Let's look at our next one here, the Laplace transform of e to the at, where a is just some number. So let's think of that as the integral from 0 to infinity of then e to the at times e to the negative st dt. Now, these exponentials we can put together using properties of exponents. I can add those, so I could go ahead and say e to the at minus st, also known as e to the a minus s quantity times t dt. Another way that I'm going to go ahead and write it for the sake of doing this problem, I'm going to factor a negative out. I'm going to say e to the negative s minus a t dt. It'll save us a step or two at the end. So let's go ahead and use our method of improper integrals. So that will actually be the limit as b approaches infinity of 0 to b integral e to the negative s minus a quantity t dt. Now this negative s minus a, that's just a constant multiple, so the reciprocal of that comes out when we do the integration. So we'll get negative 1 over s minus a. We'll keep this exponential, e to the negative s minus a t. We'll evaluate from 0 to b. So let's go ahead and think about what happens when we plug in b. Now you've got a bunch of letters in here, just make sure you're plugging in for t, right? We integrated dt. So we'll get the limit as b approaches infinity of negative 1 over s minus a, and then here this is e to the negative quantity s minus a b, minus what we get when we plug in our lower bound 0, which would be negative 1 over s minus a, and if I plug 0 in for t, then that's just going to give us e to the 0. And now let's look at what happens over here. The issue is what happens with this exponential. It depends on what s minus a is. If s minus a is a positive number, then we would have a negative some multiple of b, right? And we would call that exponential decay. If this were s minus a were negative, then we would have negative and a negative, making this a positive exponent, and that would be exponential growth. It would have infinite growth, right? So if s minus a, let's write this down. If s minus a is negative, then our limit here is going to diverge. And I don't think that's what we want. We actually want some sort of a real valued function here. So if our s minus a is positive, then we will have this limit converging. And as long as s minus a is positive, then this limit is actually going to go to 0. So we'll say this converges to 0 then. And so then our entire answer here depends on our second thing. So we'll go ahead and say s minus a here really needs to be positive. In other words, greater than 0. Another way to say this would be that s needs to be greater than a. So as long as that's true, this becomes 0. And then it's just going to depend on the last term, negative and minus. We'll get plus here. E to the 0 is 1, so we just get 1 over s minus a, as long as s is greater than a. So our Laplace transform, based on this little inequality here, for e to the at is just 1 over s minus a, whatever was in your exponential there. For the Laplace transform of sine of some multiple of t, then that's just going to be the integral from 0 to infinity of, I'm going to go ahead and put my exponential in front this time, e to the negative st sine of kt. I think I just prefer the way it's written that way. You can put your sign in the front if you'd like. We're going to have to do this by parts twice, and it's actually going to repeat once we do it, so we've got a lot of fancy stuff going on here. So in this instance, I'm going to choose u is equal to e to the negative st. That means my dv in this case is going to be sine of kt dt. Our du then is going to be negative s e to the minus st dt. And if we integrate this, v will actually be negative 1 over k, because of the constant multiple in there, cosine of kt. Since I'm going to be doing a bunch of integrals here, and we've got repeated integrals, I'm going to go ahead and leave my bounds off and come back to them. So we'll come back to this 0 to infinity later. So we'll go ahead and say the integral of e to the negative st sine of kt dt by itself without any bounds. So that will be uv, which will be negative 1 over k, e to the negative st cosine of kt, minus integral v du, minus, I have a negative and a negative, makes that positive. I have an s and a 1 over k, so that becomes s over k, integral, and then we have an e to the negative st, and we have a cosine kt dt. So now we'll need to do this integral here. I'm going to choose my same thing for u. I'm going to choose e to the negative st. My dv this time is going to be cosine kt dt. Du is going to be the same thing than it was last time, negative s e to the negative st dt. And if I integrate cosine kt, 1 over k is going to come out, so we'll get 1 over k sine of kt. We'll go ahead and write down what I already had here, negative 1 over k, e to the negative st cosine kt, minus s over k, and then from this integral here we get uv, which is 1 over k, e to the negative st sine of kt, minus integral v du, minus, now we have a negative here as part of v du, so that makes that plus. S and 1 over k will give us s over k. Integral of e to the negative st sine kt dt. And you can see, I think now, if I bring this down, we actually ended up with the same integral we started with. So if I go ahead and simplify this a bit, let's at least distribute here. We'll say negative 1 over k e to the negative st cosine kt. Here we'll get negative s over k squared e to the negative st sine kt. Distributing this here, we'll get minus s squared over k squared times this integral that we started with. And so now we just want to look at combining like terms. So we have this integral exponential sine kt here and here. So I'm going to go ahead and add this to the other side. So we're going to add s squared over k squared times this integral to both sides. That's what we're going to do. And if we do that, on the left side here, this is really having a 1 here. So you have 1 of this integral plus that. If I think of this as k squared over k squared, and I add those together, then we actually get k squared plus s squared over k squared times this integral on this side. And we won't have this anymore, so we just have these two terms. Negative 1 over k e to the negative st cosine kt minus s over k squared e to the negative st sine kt. And then to solve for this integral, what we're really going to do is just multiply the reciprocal of this over to the other side. So we'll actually get the integral of e to the negative st sine of kt dt is equal to k squared over k squared plus s squared times all the stuff we have over here. And then we need to put our bounds back in once we've done this. And so we'll go ahead and do that so we don't have to write this all again. We'll just go ahead and put our equal to the limit as b approaches infinity of all of this stuff here from 0 to b. Let's go ahead and see what happens when we use our b approaching infinity. So we'll have this constant multiple. We'll have k squared over k squared plus s squared. And if we put b in here, we'll actually get negative cosine of kb over ke to the sb minus s times sine of kb over, I'm going to go ahead and bump that down as well, k squared e to the sb. So that's our plugging in b minus what we get when we plug in 0. So if we plug in 0, think about what happens. We'll get cosine of 0, which is 1, so we'll have 1 on the top. We'll have e to the 0, so we just get 1 everywhere except for this 1 over k, so we get negative 1 over k. And if I plug in 0 here, sine of 0 is 0, so actually all of this just becomes 0. And so now let's look at what happens when we take the limit as b approaches infinity. These cosine and sine functions are just wavering between negative 1 and 1, but these exponentials in the bottom are heading off toward an infinite value, right? So we get some constants in each of these over something infinite, so both of these are going to go to 0. And then so really we just get minus negative 1 over k, so everything in here in the brackets is actually just 1 over k. So if we simplify this, we actually get k squared times k squared plus s squared times 1 over k. And if I reduce one copy of k squared with this k term down here, and I write this in a different order on the bottom, we get k over s squared plus k squared as our Laplace transform for sine of kt. We'll walk you through one more here, Laplace transform of hyperbolic sine of kt or sinh of kt. I'm going to go ahead and this is not nearly as long as the last one. The last one was the monster of the video. I'm going to go ahead and use the exponential definition for hyperbolic functions. So sinh of some multiple of t is e to the kt minus e to the negative kt all over 2. So I'm going to go ahead and use that. I have an over 2. I'm going to go ahead and bump that 1/2 out in front of my integral. So I have 1/2 integral 0 to infinity, and then it will be this e to the kt minus e to the negative kt. E to the negative st dt. So this looks nice because now we can use properties of exponents, I bet. So I'm going to go ahead and distribute this in. So we'll say 0 to infinity, and then we'll have, if I add these exponents, that would be e to the k minus s t minus, and then here if I add those in, that would be, I'm going to actually factor the negative out front and say negative k plus s, since they'd both be negative, t dt. And now these aren't so bad, those are just exponential functions. So let's go ahead and set up our limit. So I'll say equals the limit as b approaches infinity. We've got 1/2, and then doing our antiderivative, we'll get 1 over k minus s. The reciprocal of this k minus s comes out. E to the k minus s quantity t. And then integrating this next one, we already have a negative. The reciprocal of negative quantity k plus s is going to come out. So I actually get plus 1 over k plus s. E to the negative quantity k plus s t. And we'll evaluate that from 0 to b. I'll go ahead and bump my 1/2 out as well. So say 1/2 times my limit as b approaches infinity. And if I plug in b for t, then we'll have 1 over k minus s e to the k minus s b plus 1 over k plus s e to the negative k plus s b. And then plugging in 0, think about, we'll get e to the 0 for each of these. So each of these is going to become 1 for the exponential. So here we'll just get 1 over k minus s. And we'll get 1 over k plus s for the second one. Now, before we get too involved in the s greater than, less than k values here, we need these to converge. If these converge, they're going to converge to 0. So as long as we have conditions where these k and s values make this converge, that's going to go ahead and be 0 there. So we'll go ahead and say 1/2 times everything in here is 0. And then distributing the minus here, we'll get minus 1 over k minus s minus 1 over k plus s. To make it so that these are not both negative, I'm going to go ahead and put this into the denominator here. So I'm going to say 1/2 1 over s minus k minus, let's go ahead and turn the s and the k around also. So it looks like s in the front and k in the back. So we get this. Now I'll need a common denominator. So I'll need to multiply in s plus k here and s minus k here. So if I do that in the first one, I'll get s plus k on the top. If we multiply s plus k and s minus k, we will get a difference of squares, s squared minus k squared on the bottom. Minus, I multiply in s minus k into the second one. I get the same denominator. And then let's go ahead and see what we have in here. So we really have s plus k minus s. So the s minus s would go away. K minus negative k would give us 2k. We'll have s squared minus k squared there. And then if we reduce our common factor of 2 there, we'll get the Laplace transform for the hyperbolic sine of kt, or sinh of kt, is k over s squared minus k squared.